Oh, there we are.
There you go. All right.
Great, thank you. So it was opportunistic that the SummerSlam event was happening this week. I just came from New York, where we had our large developer event on Tuesday this week with about 10,000 attendees there at the Javits Center. And I've got to go to Seattle next week for something else. So I thought I would fly up here, steal a speaking opportunity from a member of my team that was going to come here and talk to you about something which is definitely, I'd say, less infrastructure related than what I understand most of the agenda is about at these events. Hopefully, try and inspire you to learn about a new topic that you might not have experimented or explored a whole lot before, which is this new application class for artificial intelligence and machine learning applications. It's one of the hottest topics in technology today, one of the hottest topics in computer science, actually, the foundation which underpins pretty much every piece of technology that we all work with. And I'll talk a little bit later about why that is the case. Why is it that there's such an explosion in interest in this particular topic area? I'm going to basically break this talk into two halves. So the first is to try and give you a flavor of how Amazon.com, the retailer, consumer products, logistics, cloud computing business, uses machine learning to run our business. And we'll talk a little bit about that. And then, of course, I'm going to connect that to some work that we've been doing in Amazon Web Services to try to make these types of capabilities more accessible for IT professionals and developers. So we'll also talk a little bit about that. And we'll talk about a couple of AWS services. I'll show you a couple of demos, try to explain to you what the tooling is that developers that are working in this particular area tend to use. And then we'll get this camera going and show you how simple it is to access some high-level prepackaged AI services. Now, I've been jumping there throughout the whole of that intro between two different terms, right? Machine learning and artificial intelligence, and that's a problem, okay? People tend to, quite incorrectly, use those two different terms interchangeably, like they're the same thing, okay? But they're definitely not the same thing. So the first thing we should do is just maybe delineate between machine learning and artificial intelligence and try and explain what I mean when I talk about those two different things, okay? So, I'm pressing my buttons.
Sorry.
Don't laugh. It's okay. So, AI, it's giving software and systems human-like capabilities and human-like characteristics, okay? So, we're talking about artificial intelligence. We're talking about getting applications to do things that traditionally, historically, you would have needed a person to do, okay? Like showing an image and describing the contents of the image. Just a few years ago, you would have to have a person to do that. You couldn't do it with software. Today, you can do it with software with a very high degree of accuracy. Understanding natural language, so using the spoken word to convey meaning to an application. Again, it's quite difficult to do. We'll talk about why it's difficult in a little while, but it's quite difficult to do. Over the course of the last 4 years, it's become perfectly normal to interact with application software using just our voice, right? So this is creating artificially intelligent capabilities for software systems. We're turning our software into giving our software, imbuing our software with characteristics and capabilities that you have normally needed a human brain, human being, in order to deliver. So that's what I mean when I talk about AI. Machine learning is the process of building all that stuff, okay? And in machine learning, you basically have three important components. You have labeled data that describes the world, okay? So labeled data in the course of, say, speech recognition might be audio waveforms, so the encoded audio that we make when we talk, combined with textual labels that describe what's been said. So a transcript, okay? So that's our labeled data. In the case of image recognition, our labeled data might be 10 million photographs of cats, all labeled with the word cat, okay? Or a whole stack of images that have got bounding boxes drawn on them that identify different objects inside a large library of visual imaging data, okay? We take that labeled data, we flow it through a machine learning algorithm. Okay, and this is an area with high complexity. There are actually many different algorithms. They are suited to different kinds of problems, different kinds of use cases. And by flowing our training data, our labeled data, through the algorithm, we create a third component, which is called a model. Okay, and that model is a statistical representation of the data that we have trained on. Okay, so it's a statistical representation of all our training data. We can then provide new unlabeled samples of data, new audio waveforms, new images, okay? And by doing a lot of maths on these new samples of data in conjunction with these models, we can return back inference, okay? The word that you just spoke was hello, from the waveform for hello, or that image contains a photo of a coastline, a yacht, and some trees, by virtue of the statistical characteristics of the data within the image. Okay, so labeled data, algorithms, that creates models. Then we use these models with new data samples in order to generate inferences, make predictions about the real world on the basis of new data samples that we get. That is what machine learning is, okay? Do enough of that and you can build systems that have artificially intelligent characteristics, understand the spoken word, extract the meaning from text, analyze images, predict the future in a series of data points that vary over time. For example, all different applications of machine learning creating these AI characteristics. So that's some definitions. How do we use this stuff at Amazon more broadly? And the answer is we use it all over the place. And if you've ever interacted with Amazon, has anyone here never been a customer of Amazon, by the way? Okay, so you've all benefited from this stuff. Now, there's a few interesting things about Amazon. I'm sure you've heard a lot about the company. One of the interesting things about Amazon is the new, unique, and I mean completely unique, worldview of the founder, Jeff Bezos. Okay, it's a very distinctive perspective on the world, very distinctive perspective on business. And one of the things that he often says is that in business, you should focus on things that are always the same. Okay, so focus on the things that never change, the things that are perennial. As technology professionals, we tend to get obsessed with change because we're working in a fast-moving area, okay? We're always having to refresh infrastructure, try to bring forward new innovations, maybe some that we think are a great idea, maybe some that vendors think are a great idea, but there's definitely a push to continually do new things. It's kind of interesting, but the problem with those investments, and you'll know this, is they actually have quite a short lifespan, okay? So if I buy technology, if I buy hardware, software, and systems, well, the lifespan of the technology is maybe 3 to 5 years. The lifespan of the maybe longest-lived enterprise applications that are out there is 25 to 20 years. It's actually not that long when you consider how long some businesses have been around and how long human beings have been around, for sure. So what we think is if you focus investment on things that are constant, that are always important, then those investments will pay back a return forever, okay? Every year that customers continue to use your product or service, if you've invested in the core characteristics of that product, customers will always find that valuable. And that's why we build things like this. This is Amazon Fulfillment Center. And this is technology developed by Amazon Robotics. So it's a part of Amazon's fulfillment operations unit that run our large-scale warehousing, distribution, and logistics systems around the world. And what you're looking at here are fully autonomous robotic systems that are powered by machine learning technology. So there's no one steering these robots around the fulfillment center. In fact, there's no one planning the layout of the inventory in the fulfillment center either. It's all done using sophisticated machine learning algorithms. And the way it works is the inventory is distributed in a quasi-random manner across the site, okay? It lives in these packing pods that you can see stacked up vertically. So inside one of those, you'll have all kinds of different products. And when you order something, there's an operative in the fulfillment center standing in one location, okay? And over the course of a few minutes, every item in your order will be brought to him by the robots. He will pick them out. He or she will pick them out of these packing cases that you can see being manipulated and moved around. He or she will put them in a tray, packing tray. That will go down a conveyor belt. A photograph will be taken. Computer vision, machine learning, and AI will be used to verify that the right products are there. Then someone else will pack it, and it will end up getting distributed out to you. Why do we do that? Why so much investment in robotics for that particular use case? Well, can you ever imagine a customer saying, I want my package to be delivered more slowly, okay? I want to pay a little bit more for it, and every now and again I want you to make a mistake in what you ship. No, I don't think so. So it's investment in something which has perennial value, which is speed, efficiency, and accuracy. And that's why we use ML extensively within Amazon Logistics. Okay, next one is about enriching existing products, okay? This is one of the most famous and longest lived examples of machine learning within Amazon retail. And this is product recommendations. Okay? It's a very large-scale data problem. Let me just give you some numbers. So Amazon has a lot of customers, okay, around the world. We also have a very wide selection of different inventory products. Does anybody want to hazard a guess as to how many different items are listed on Amazon.com in the US right now? How many different products do you think there are on the Amazon.com website? Anyone know? 1 billion? It's a little less than that. There are just north of 200 million unique item listings on the website. Now, I don't know if anybody's done work on data management, relational databases, non-relational databases, maybe even software engineering around creating data structures for systems. But consider a model, a data model, with every Amazon customer down one column, okay? And then 200 million more columns in this table, okay? We'll talk about how difficult that is in a second. And then you've got intersects, where a customer intersects with a product in a particular cell in this table, okay? And where you've purchased something, you have a non-zero integer in the cell. I've bought between 1 and x of that particular item. That's what you call a sparse matrix from a data structure perspective, right? Most of the table is what? Well, most of the table is empty. Most of the table will never be filled. Even my children will never buy 200 million items. They'll have a go, but I don't think they'll get there, okay? So you've got this challenging data structure that you need to deal with, and the machine learning problem here is, I've got a purchase history of 500 items. Based on my recent purchasing history, what's the 501st cell in my row that's going to have a non-zero integer in it? So I'm trying to predict that, okay? I'm trying to predict the next cells that someone that bought this particular product also bought. So I'm trying to find affinity between customers' purchasing history based on a learning algorithm that understands and learns about what other customers have done. Okay, so that's how you build a system like this. It uses a specific machine learning technique called it's a sparse vector matrix for the data processing and then a factorization machine for the actual algorithm. And that allows us to look at a sparsely populated matrix, draw commonality between the rows in that sparsely populated matrix, and make predictions or do inference about what the next most likely populated cells are going to be given the current status of any one row. Okay, so it's a specific machine learning algorithm that does that. There are academic papers and lots of examples of this being used out in the wild. Another very, very famous Amazon customer that uses that is Netflix. So for movie recommendations, which generates, by the way, about 75% of all of Netflix's traffic, they're using exactly the same algorithm, but they're using your watching history rather than your purchase history. Okay, so very popular. Has anyone ever bought anything from the recommended items tab? And has anyone ever noticed how amusing it can be at certain times of the year? Like when I look at this in January, okay, it's all Lego Friends and girls' gymnastics equipment, which should give you a flavor for how young my daughters are. So that's basically what we're into in my house before Christmas, and that's what my recommendations look like for the January, February, and March period until it's been filled back up with software engineering books. So yeah, there you go. So it definitely works, and there's also a lot of funny stories about how it works as well. Right, video. Talked a little bit before about image recognition, video data extraction, audio transcription I also mentioned as well. So how might we combine those kinds of features together to build a cool product? Well, over in Amazon Prime Video, we have quite a few features that use these techniques. One of them is something that's really, really cool with these new, well, not so new in the US, epic TV shows that span multiple series and have seasons and have, hundreds of characters in them, like Game of Thrones, okay? We've got many characters there. If you've read the books, you'll know that actually the character count in the TV show, the adaptation, is relatively low in comparison to the novels, but it's still very high for a piece of work like this. And it can be very confusing for watchers that come to these kinds of content series later in their lifetime, I start watching in series 4, and I really don't know what's going on with Khal Drogo. I really don't know what's going on with Daenerys Targaryen. I want to know what the backstory for these customers is. Well, we built a feature in our video service that allows you to do that. We do a few different things. We play the audio from the video through a transcription service. So we can convert it into text tokens. Okay? We can extract words from the audio waveform. Then we do video recognition with facial recognition, object recognition, and object tracking. Okay? And we can tie these analytical workloads back to the time series data that's associated with the video stream. And we can then allow you to do something like watch the story of Khal Drogo, extract all of the dialogue where he is mentioned, extract all of the video segments where he appears, and reconstruct Game of Thrones around one particular character. But we can do that using a machine learning technique called unsupervised learning, which means nobody ever has to tag any frames. Nobody ever has to say, this is an important character. The algorithms figure out who the important characters are from the frequency of the appearance of terms in the transcript, the frequency of appearance of those characters in the video, and they build what you call the topic hierarchy, okay? And they decide which topics should feature in these reconstructed narratives that are built using this service. So no supervision, unsupervised machine learning for building new features in video products. It's quite an interesting and very innovative use case. Also works inside the iPad app, so you can freeze frame. If you're watching Prime Instant Video, you might have seen this feature called X-Ray, which pops up on top. You can click these buttons. You can see all of the other movies, TV shows, maybe authorships that the characters might hold from IMDb, which is extracted from that. You can also watch or listen to, it's going to work for me? Looks like not. Watch or listen to the soundtrack, which we extract using similar kind of techniques for audio fingerprinting as well. So that's in video. And then we're getting into the experimental domain, brand new products and services that have, have never been done before. This is cool.
These modest-looking buildings contain innovative prime air technology. Here's how it works. Moments after receiving the order, an electrically powered Amazon drone makes its way down an automated track and then rises into the sky with the customer's package on board. These drones are autonomous. From takeoff to landing and
These drones are autonomous.
operate
Just remember that.
completely on their own.
Okay, I'll come back to that in a sec.
Cruising quietly below 400 feet, carrying packages up to 5 pounds, and guided by GPS. Our systems are designed to find their destinations safely. Within 30 minutes of placement.
So autonomous flight. This is a trial which is operational right now in Cambridge in the UK. It's a university town, as you'll know, about an hour's north of London by high-speed rail, by train. And it's a trial in a rural area, okay? So the pace of change in the landscape here is, relatively slow. Where would autonomous flight have real high value? Well, it's in urban areas, okay? The built environment can obviously change very quickly. If you've ever been, I went to New York this week, it just seems like there's construction everywhere. It's the same in London, construction everywhere. Over the course of a couple of days, you can have a whole forest of cranes appear. Over the course of a month, you can have a tower appear. All that construction equipment disappears, and then you've got a new landmark in the city that, for an autonomous system, a flight system, is actually something that needs to be carefully avoided, okay? So we're using quite a few techniques here. We're using machine vision, of course. So on the drone, there are cameras that allow the drone to autonomously avoid hazards in the environment, in the built environment or in the physical environment. Power lines, trees, cranes, buildings, vehicles, even on landing, potentially could be something that we want to avoid. But it's autonomous, so we don't have connectivity to the cloud, can't guarantee or rely upon connectivity to the cloud for the purposes of this particular application. So what is challenging about that? Well, we're evolving a product where we want to train and enhance and optimize these machine vision models very quickly, so we can quickly enhance the product using iterative approaches. The second thing is, battery is directly correlated with flight time, right? What do we know about CPU technology and battery? The more your CPU runs, the more battery you use, ergo the shorter the potential flight operational time for the drone is. So we need very power efficient CPU technology, and we're doing these high performance, high demand calculation operations that are required to do computer vision. So it's a kind of difficult confluence of different requirements. High precision, rapid computer vision in a low power environment plus the ability to iterate on these models very rapidly. So I actually created a brand new service at AWS called Greengrass ML. Allows me to run a runtime on a low-power Intel or ARM CPU, and it allows me to do controlled deployment of machine learning inference models down onto that runtime and have them operate autonomously of the cloud. Okay, so we use the cloud for deployment to push the code, push the models down to the endpoint, but after that, we don't use it. The inference, the predictive analytics, the machine vision in this case, all takes place locally and autonomously on the device, on the disconnected or connected device. It doesn't actually matter. It will operate either way. Okay, so that's a very, very interesting use case with some very unique characteristics. And then there's this lady. It's funny that you can talk about a connected speaker and it is gendered. Okay, so this lady, Alexa, one of my friends, my best friends, I'd say, in every home in my house, pretty much. This is something that people feel unusual the first time they use it, okay? Anybody heard the phrase AGI, Artificial General Intelligence? Like Skynet? Yeah? This is not what Alexa is, but people believe that it is because the act of communicating flexibly in a natural way with something that is artificial, something that is fundamentally software, it's very, very new to a lot of people. It's very, challenges a lot of preconceptions. Communicating using speech, well, it's normally something we associate with humanity. With part of the essence of being a human is that you understand speech. We're the only things that do that. Animals don't do it. Well, they might do it, okay, but they certainly don't talk back, okay? This device will understand you. It will ask you questions. It will adapt to the flow of a conversation to enable you to use the product, use the system to fulfill intents. What's the weather in Portland, Maine? How's my flight on Delta from Portland, Maine to New York later today looking? That's a very sophisticated sentence, by the way, that I just used there. How's my flight? Is flight an entity, or is that part of the intent? From Portland, Maine to New York, so I packaged up an origin and a destination in one utterance. Later today, it's a time and date reference, but it's not something that a machine would recognize as an ISO format date. Building a system like that is really, really hard, okay, that can have that single utterance, that single shot detection of what I mean, what I want, what the important entities are in the right order, and then propose a question back to me like, your flight later today is actually canceled. I'm sorry. Do you want to rebook for tomorrow at 8 a.m.? So there's back-end logic there, which is going to reach out into other systems that reflect the current state of the world. It's going to construct audio, it's going to send it back to me, and it's going to do that rapidly enough for me to feel like I'm talking to a person. So under the several single-digit 100 milliseconds response time. It's actually very difficult to do. So I'd say this is the closest thing to science fiction that we have in consumer technology today. Okay? Very, very interesting product. You can extend it. I'm sure, has anyone here experimented with Alexa skills development? You should do that if you haven't. So you can basically power up your own Alexa and deliver applications on it. They could be fun applications for home. In fact, I have a friend, Drew Furman, who is an AWS community hero. It's one of our analog for vExpert, essentially. Okay? His daughter has written a couple of skills, riding a popular wave to do with a fictional wizard from the United Kingdom called Harry Potter. I don't know if you've heard of him. Quite well known. And her skills generate her money every month. She receives a royalty check from Amazon for driving usage of Alexa with the popularity of these skills that she's developed, using the Alexa skills kit and deploying onto the platform globally, and any person that owns an Amazon Echo can activate these Harry Potter. I think there's one sorting hat skill. Will tell you whether you're, good with Gryffindor or slightly suspect with Slytherin. Okay, so definitely check those out. And if you're a developer of any type, or you want to experiment, maybe you want to rediscover development capabilities that you've had earlier in your career, Alexa skills and voice application development is a really fun and interesting way to do that. Really, really easy to get started with as well. It's an extensible platform for building these kinds of apps. But we take care of the hard stuff around voice recognition, intent resolution, entity extraction, sending you data structures that your simple software can process in order to drive the business logic that's required to fulfill transactions and provide entertainment experiences and everything else that you can do on this platform. Really, really interesting product. And then lastly, for this set of examples, we have this. Work? Oh, no, go back. Maybe this is the non-animated version. Oh, there we go. Okay. So this is a retail store in Seattle called Amazon Go. A lot of people have heard about this now. It was open to Amazon employees as an experimental internal test for a long time before we opened it to the public early this year. Okay, and the experience here is you walk in, you get the Amazon Go app on your phone. You probably just saw that guy do there. It's got a QR code in it. You hold it down on the scanner. The gate opens. You walk inside. Okay, you get your Nitro Espresso coffee, or I'm in Seattle here, okay, so I can definitely have one of those. Chicken salad, a beer, walk out. 90 seconds later or less, you get a notification in the app saying, we've just billed you $12 for a Nitro Espresso coffee, chicken salad, and a beer. No checkout, no barcode scanners, no noticeable RFID in the environment, nothing, just machine vision, what we call sensor fusion in the environment that allows us to match who's taken what product to create an entirely new retail experience, and one that customers actually really, really like, okay? Lots of sophistication here. What is quite interesting about it is it's actually underneath an Amazon office. So if you are in Seattle and you do go here, and you can go, it's completely open to the public now. Just get the app, link it to your Amazon account, go in and try it out. You're underneath an Amazon tower called Doppler, okay? And Doppler is the pre-release code name for the Echo. All of our buildings are named after substantial, important Amazon products and projects that we've run. So yeah, check that out. It's great. Machine vision, sensor fusion, and it's a very sophisticated system able to overcome attempts to game the system, like taking a product, putting it in a bag on the floor, taking another product out of the bag that you've previously taken off the shelf and then walking out. It will not be gamed by that. Or coming into the store dressed as a 6-foot-tall banana, taking a load of products and walking out. It will perform object tracking on bananas as well as humans. It's very, very sophisticated. This is Halloween in the US, and this was something that we saw happening during this pre-release trial. People were trying to game the system by using costumes, superhero costumes, giant pieces of fruit, all kinds of stuff. But it does work. It can detect which banana's taken what product. Yeah, very good. Okay, so that's all about machine learning, artificial intelligence at Amazon. I hope that's inspired you to think about what's possible. Maybe you didn't know that some of these capabilities and features use this kind of software technology at the core, but they're all built using AI and ML, and we'll have a lot more stuff in the future that uses the same kind of capabilities. How long have we got? 30 minutes. Who knows why Amazon Web Services was created? AWS was created initially because within Amazon, we were finding that it was getting harder and more expensive for us to develop software, the software that we needed to run our business. Okay? So we thought about all of these different teams we've got are using the same low-level primitives. They're all using virtual machines. They're all using storage. Okay? Can we turn those things into reusable services so that we can give our builders, our software developers, our architects, immediate access to the resources that they need without having to wait for them, and also create an efficient pool of resources so that if my project is not successful, I can just stop using whatever I'm using, return those resources back to a pool, okay, common term in virtualization, of course, but the cloud really invented it, and then take those resources back from the pool and use them for another project. Okay, so we started thinking about this, and like everything we do at Amazon, we start and finish with customers. Customer obsession is one of our key values, our leadership principles, as we call them. So we started thinking about, well, if we've got this problem and it's going to help us in our business, develop our own software products, build the technology, run the technology that we need to create new services for customers, maybe some of our customers, we were thinking here really about marketplace sellers in the first instance, people that were listing inventory on the Amazon retail websites, maybe they will also find those things useful. Okay? It turned out we were right, and Amazon Web Services is the $22 billion run rate business 11 years later. So we were onto something, we validated it, and it turns out we were able to catalyze a wave of change in the IT industry that's probably unprecedented. This is as big as the shift from proprietary to x86, or as big as the shift from mainframe to distributed computing. That's how big cloud computing is at the macro level. Okay, we'll change everything you know about technology. Probably already has changed everything you know about technology over the course of your career, okay? And it will continue to do that for the foreseeable future. So this is big, okay? And it's big because of the fundamental characteristics of the cloud. Stop doing things that do not help you deliver your mission, do not help you build the products and serve the customers that you want to serve, that your organizations want to serve. If it can be turned into a utility, if it can be automated, if it can be delivered at huge scale with continuously falling costs, then use that. I know it's something that can cause challenges in the context of technology professionals, but it really does provide a better way to build applications, okay? And that's in the resource area where your simple need is, I need machines, and I need storage, and I need networks, okay? We're doing exactly the same thing, trying to do exactly the same thing for other challenges that are faced by people that are building software and systems. So isn't it natural that we're trying to do the same thing with machine learning and AI? We're trying to identify the things in machine learning, the machine learning process, and in the creation of AI applications that are common, the things that every developer uses, the things that every developer needs to do in order to build these kinds of apps. And we're trying to turn those into reusable services that all of those developers can just access. So rather than having to build their machine clusters, rather than having to tune and optimize these algorithms, rather than having to store huge amounts of data in different places and move it around, we can deliver all of those different components as a set of reusable tools that developers can just consume. That's what we're about, okay? So putting ML capabilities into the hands of all developers that want to use it. Now, this is a very interesting aspect of this particular talk track. There actually are more than one class of user. Talking about developers, I'm talking about developers all the time, right? It's my job. And I've been a software engineer, spent a long time in infrastructure, and returned to software engineering when I came back to Amazon. There are many different types of customer. We recognize at least 3 different types of customer that we're trying to serve here, okay, with different types of products. So we're going to get more technical here. In the bottom layer, we've got, who's heard of TensorFlow or Apache MXNet or PyTorch? Okay, these are the tools that are used in running this machine learning process. Got my annotated data, and I want to create a model. What does that? Well, an algorithm. And these tools like TensorFlow and PyTorch and MXNet, they're mechanisms for creating the algorithms and running the algorithms in a flexible, scalable way. Okay, and I'll talk more about deep learning neural networks, convolutional neural networks in a second, because that is something we need to talk a little bit about. You'll understand why the infrastructure looks the way it does when we talk about some of the fundamentals for this approach, okay? So we've tried to make it as easy as possible for experienced and expert developers, like the people that just put their hands up, to access the resources that they need to run these algorithms at scale. Then in the next layer, there's another class of developer. Until last November, confession, never actually touched any ML-related development. Okay? Done a lot of software development, mostly in tools. In fact, my first job was writing bootstrapping tools for Silicon Graphics IRIX, kind of like Puppet or Chef for SGI IRIX 5.3, so it's a long time ago now, an operating system which is pretty much dead and gone. That was my first job, and I did a lot of systems programming, but I never really touched AI or machine learning, okay? And the reason for that is it's hard, okay? So it's difficult to do. So what are we trying to do? Well, we're trying to bring tools forward that mean it's not hard anymore. And I'll give you an example of that in a second. I'll show you a notebook, which is a data science tool that I've created to enable me to build a simple machine learning app. And I'll walk you through the different components and explain how I use various AWS services to do that. That's SageMaker, Amazon SageMaker. It's our tool for creating kind of like an SLDC, Software Development Lifecycle Management tool for machine learning models. Okay, so help customers iterate on those models more quickly. And at the top, I don't care about any of that. I'm not just a developer. I'm a web developer. Okay, I deal with presentation. I deal with JavaScript. Okay? But I want to have machine learning capabilities in my app. I want a web application that has facial recognition. I want my web application to speak with natural language. I want to integrate chatbots into my web app. I want to analyze natural language inside my web application and return results back to users. Okay? But I don't want to deal with any of this stuff. I don't care about models. I don't care about training. I don't care about annotated data. What I care about is sending my beautiful JavaScript objects to this endpoint, okay, and getting back a result. That photo's got a picture of a cat in it, for example. Okay? So that's what this top layer does. Application services. We're on. Here we go. application services that make it really simple for non-machine learning developers just to call APIs that deliver AI features, native AI features, okay? We'll talk quickly about a few examples of customers that are doing this, and then we'll dive a little bit more into deep learning and what deep learning is. So turns out AWS was incredibly popular for running these kinds of applications before we started creating services that were specific for them, okay? The main reason for that is we had a particular type of EC2 instance, virtual machine family, called the P2, and inside this P2 was the last generation of NVIDIA FPU. So you've heard of a GPU, probably your kids or you have them in your gaming rigs for playing Fortnite or Far Cry 5 or whatever you're doing right now. Well, going beyond that, having way more capacity than you would ever need to render a page of graphics or a screen full of pixels is something called an FPU, okay? It's mass parallel computational floating point units, very important for deep learning algorithms, and I'll explain why in a second. So we had that for a long time, this P2 instance family. Lots of customers that were using TensorFlow, that were using Caffe, that were using other machine learning tools, were using AWS for this. Customers like Pinterest. Anyone use Pinterest? Image search, right? You can type in the name of an item, and it will return back to you images that have that thing in them, right? Like a candle or garden furniture is one that I've used when I was redoing my yard, you call it here, right? My garden. Searching for garden furniture would give me a load of pictures with different types of tables and parasols and stuff in it. No one's ever labeled those images manually. No one's ever picked out all of the garden furniture images and said, oh, here's a new picture with garden furniture in it. No. There's one of these neural networks there that is trained to recognize garden furniture, yachts, racing cars, houses, patios, all kinds of different labels, and then they use that to figure out what's in the images and present them back to your image search so you get back the image category that you want. That's Pinterest right here. The whole thing's built on AWS and running on AWS. It's absolutely massive in terms of usage. Okay, Netflix, recommendation systems. And then we've got some other ones which are interesting. Royal National Institute for the Blind. With a name like that, it's only going to come from Canada or the UK, right? Well, it comes from the UK. It's a non-profit that supports people with serious visual impairments, and it makes content accessible to them. So what they do is take our service, Polly, which is a text-to-speech rendering service, kind of like the engine inside Alexa that generates the voice for you. But it's open. You can send it a corpus of text and receive back an MP3 file or an audio stream a few seconds later, which has got that beautifully spoken 27 different languages from around the world, well over 50 different voices, adults, children, fine-grained control over pronunciation, over pro-rhapsody, which is the talking speed. You can make things sound more impactful. You can whisper with this service by marking up the text that you send to the engine, and you'll receive beautifully rendered audio back. Okay, and they use this for making content accessible to people that unfortunately can't read because their sight is too degraded for it. Okay, so lots and lots of usage of these services by customers of all types. FINRA, the financial regulator of North America, anomaly detection. Okay, they're ingesting billions and billions of trades for stock, securities, derivatives, all kinds of products every single day. They're converting, checking those against what considered normal statistical patterns for those activities, okay? And then they're firing the ones that look like they might be questionable over to a human being for investigation. There's something that looks like it's outside of the normal pattern for this particular time period or this particular security type. Shouldn't we investigate that with a human being? So that's machine learning for anomaly detection with FINRA also running on AWS. Okay, all over the map, different use cases that you can see. Okay, let's just talk about this low-level stuff, and then we'll jump out and do a couple of demos. So I mentioned before about these low-level primitive components that are important for experts that are building systems of this type. Of course, we build our own stuff on these as well. So if you're using one of our frameworks, say SageMaker, you can use these same kind of low-level resources to run it. You'll get very good performance on your model training, very good performance on your inference. Maybe the first question to ask here, first thing to talk about is why is performance in model training important? Who's moved from waterfall, or whose organizations have moved from waterfall to agile methods? Why did you do that? To be quicker. And why is being quicker important? You've got to be first to market, but there's something else as well. The more quickly you can ship software, the more opportunities you have to make decisions about the software. So if I've got one 3-year-long project, and over the course of those 3 years, the requirements for my project change, how much value does my project deliver at delivery point? Well, somewhere between 0 and a number which is less than originally forecast, right? Because it's no longer a fit for whatever the people that thought of it had in mind when they created the project. It's taken too long to get to delivery. And in that time, the context, the situation around the project has changed. So it's less valuable at the point of delivery than it was when we thought of it, okay? But what if instead of doing that, we're shipping a version of the project, even if it's a reduced functionality version of the project, every 3 months, or every 8 weeks, or every 4 weeks? After that sprint, we can evaluate what's the next most important thing we have to do, and then we can do that, right? So it allows us to track more closely to user requirements without having this requirements drift, where we think of an idea, but by the time we deliver it, it's not as valuable as we thought it was when we started, okay? And it's exactly the same in machine learning, but for a different reason. We want to compress down the delivery time for these systems because they're experimental systems quite often. When you start the process, you might not be able to solve the problem that you want to solve using the technology. Sounds kind of counterintuitive, right? But I've got a hypothesis here, an idea, a belief that I can solve this particular problem by applying machine learning to it. What if I'm wrong? What if I selected the wrong algorithm? Or I tuned that algorithm in the wrong way, so I didn't get the output, the outcomes that I thought I would get? Well, if it takes me a long time to do that, it'll take me a long time before I can try something else, which might work. So I want to compress down the iteration time at the kind of fundamental level for building these models. So performance is really important here. Having the fastest, largest pool of machines available to you to run the training will mean that you can get your results back, your effectiveness score back that much more quickly. And then you can keep that if it's a good outcome, or you can try and improve it if it's not as good. Okay? But if it takes you a long time to get to that first answer, and then a long time to get to subsequent answers, it'll take you a lot longer to get to the right answer. So speed is important, and compressing this down is important. To give you an example in another field, this is why geneticists experiment with genetics using fruit flies. Because you can breed a generation in a matter of a few tens of minutes, and then observe and breed another one, observe and breed another one. It's the same with software, weirdly enough. The less time it takes you to get the results, the more quickly you can adapt. Okay? So in here, we have this stuff. I mentioned P2s before. We ship this now, which is called a P3. This is 40,000 floating point cores. Okay, so a high-end NVIDIA graphics card has between 6 and 8. Okay, we got 5 times that. You couldn't get a video screen big enough to make it worthwhile to use this for Far Cry 5 or Fortnite. Okay, there isn't a monitor out there big enough to use all that horsepower. But in deep learning, these things are golden. I'll explain why they are. So I've talked about deep learning quite a bit already. So the classic use case here is something like image recognition, okay, which I'll show you a little bit later on. I have an image. What is an image in a computer? It's an array, okay? However many pixels I have in my image, in a square array, yeah? And then each one of those pixels has got color values in it, RGB, red, green, blue, with a certain amount of precision. In the web, we're normally using 256-bit red, green, blue. We move those sliders around as you might, and aligning them differently creates a different color, right? Just like mixing paint in a middle school creates a different color in the different ratios that you use those colors. It's the same in an image. So I want to evaluate what's in an image. I've got all my input data, which is all of my pixels with all these color values. That, in deep learning parlance, is what I call my input layer. Actually flatten it out. So instead of having a square, okay, I just have a massively wide line of numbers, massively wide line of cells, each one of which has got 3 numbers in it, a red, green, and blue value. With me? Okay. Then, what I want to do, ultimately, is generate a distinctive statistical output, numerical output, for images that have different characteristics. So all of my images of yachts, all of my images of coastlines, all of my images of cats, my hypothesis is I can do something with maths that will allow me to draw similarity between all my images of cats, similarity between all my images of yachts, and similarity between all my images of coastlines. I believe that there's something that all those images have in common, right? There must be, because I'm going to reverse those numbers and produce the labels from the reverse numbers. So I must be able to use, in programming terms, a set of functions to sort of distill or boil down this data into something which is distinctive for different classes or types of images. Believe me? Well, I can tell you it definitely works because this is how deep learning works. So this definitely works. This hypothesis definitely works. The thing that's difficult is we're constructing this wide input layer with all these numbers in it, yeah? And then we're going to perform transformation functions on that wide input layer of numbers. And that might be 1 million or 16 million different numbers in the top layer, so 16 million wide, okay? And I'll just say that the state of the art in image recognition right now is something called ResNet, which is winning a competition a few years ago for computer vision. And there's many implementations of the ResNet algorithm. It was written up as an academic paper, so anybody can take it and implement it. There are 127 layers of calculations in ResNet. Each one of those layers takes that 16 million input numbers, each one of which might actually have 3 values in it, remember that, okay? And it transforms it. It adds those numbers together, it calculates vectors based on those numbers, it passes them down to another layer in the deep learning network. This is why it's called deep, because it has a lot of layers, okay? And at that layer, there's a load more transformations. And at the next layer, a load more, and at the next layer, a load more, and at the next layer, a load more. So you get a data structure which allows you to flow data through it, transforming the data at each layer, and at the bottom, you get an output layer, okay? And on that output layer, you match that output layer against those labels that originally define the input data, and you find your correlation there. The output layer looks like this for a yacht. It has these characteristics for a yacht. It has these characteristics for a cat, and it has these characteristics for a coastline, okay? And then when we put our next sample in, flow the data from that sample through the same network, look at the output layer, we can say, oh, that looks like a cat, because it's got similar characteristics to all the other cats that we've seen. That's basically how deep learning works. 127 layers, 16 million pixels or more, 3 values per pixel. Every layer has a stack of calculations. Typical training set, how many images do you think we might train on if we want to build a good model? 150 million. So we've got 150 million labeled images that we need to flow through this network, doing all these calculations on, to spit us out these statistical models that we can then analyze. Do you now know why you need a GPU? Do you now know why you need 40,000 floating point cores? You need as much computational computing power as you can throw at the problem to solve this kind of problem in a quick way, okay? So this is why we talk about low-level building blocks. It's actually fundamental to doing this in a way which is anything like timely or anything like performant, okay? So that's a lot of talking. Let's show you one more thing, and then we'll jump into 2 very quick demos. You'll indulge me on the demos. So, mentioned SageMaker earlier. I'll just tell you what that is, because I'm going to show you it in a second. So, I've talked really so far about applications of AI and machine learning in Amazon. I've given you an intro to deep learning neural networks. Okay, so that's one machine learning technique that can be used. It's typically used with data sets that have high complexity and very high numbers of features. Okay, features are characteristics of the data set. Think of them as records in a database, in your schema, maybe, okay? There are other things you need to do, though. So talked before about data prep. You know, my labeled images. If I'm training for something like ResNet, I'm fortunate there's something called the Berkeley Image Commons, which has 150 million pre-labeled images in it, which are in the public domain, okay? But maybe that's not what I'm doing. Maybe I'm trying to do something relatively simple, you know, like predict the future price of a security, or predict the future price of a utility like energy, natural gas, or power, for example. Quite a simple data set. I've got time series data indicating how the price for that particular commodity, that particular item, has varied over time, right? It's going to look like a waveform probably, or some sort of linear chart which goes like this. And for that, I might want to predict the value of that variable at some point in the future. So I'm not going to use a CNN, a convolutional neural network for that. I'm going to use a different kind of algorithm. The specific one we have is called deep AR, okay, sequence prediction. It uses neural networks, but it's much, much simpler than the kind of stuff that you would use for image recognition, for example, okay? So I've got my data. I need to aggregate my data together with one of these algorithms, and by doing that, get my results back, and then I'm able to make predictions about the future. That's an iterative process, as I mentioned. What we do with our SageMaker service is encapsulate the different steps of that iterative process inside a tool. So have some tools for data preparation, enabling me to clean up my data and do experimental small-scale training with samples, just to prove that my algorithm works. I can ingest the data and get a model out. Probably not a very accurate model, but I can get a model out. Then, training at scale, apply the different frameworks that are available to the problem with a pre-built, pre-optimized algorithm that allows me to build an accurate model with a large data set. Okay? Quite often, this is parallelized training, so running large numbers of machines in parallel, each one of which working on a part of the training set with the models, with the algorithms rather, and creating part of the model, which is then reconsolidated at the end to build my accurate predictive model. Okay, so that's what this stuff does in here. Okay, and then at the end, I want to deploy that. So it's not an academic exercise, right? I want to use that model for inference in the real world. If it's image recognition, maybe I want to moderate images on a website and remove those that might have questionable content, for example. That's an example use case. If it's sequence prediction, maybe I want to have a website that allows a consumer to enter their own energy bills over time and predict where their energy bills are going to be in a month or a year's time based on this forecasting algorithm. See, so it's the use case that matters. And I need to expose that to a customer as an interface component within my application, right? So we're not just doing this for fun. We're actually trying to build features that are valuable for customers using this technology. The last part of this is deployment. It allows us to create API endpoints, so contract endpoints, that we can send data samples to and get results back. An individual consumer sending in their energy bills over the course of the last 2 years and receiving a prediction about what they'll be next month, for example. Okay? And for that, we have deployment capabilities where you can drop endpoints with these capabilities into AWS and use them with your applications directly for inference. Okay, 2 quick demos that I want to show you. This will probably overwhelm some of you that have never seen data science tooling environments before because it can be a bit heavy, I'll warn you now, okay? Maybe you already think the talk's a bit heavy, but this can definitely get heavier. So this is a tool called the Jupyter Notebook, okay? This is an interactive environment for data science. It allows me to write code, normally Python, with a library called Pandas, which is used for data manipulation. It's a little bit like a programmable spreadsheet. I can load my data into something called a data frame, which is sort of in-memory representation of a table. Then I can manipulate it using commands. Okay. Very similar to another language called R, which I'm sure a lot of you will have heard of, which is generally known as the statistician's programming language for data analysis. Okay. So what I have here is an example notebook that uses this tooling. You can see that I'm importing, put that way. You can see that I'm importing various modules here into my environment to enable me to work with and manipulate data. And I'm loading a data set from Amazon S3. This data set happens to contain my own social media data. So it contains my history on twitter.com of posts that I've made, popularity of those posts, and actually other metadata about those posts. You can get this data set by going to Twitter Analytics and clicking Export Tweets. You get a large CSV file that contains all of your data. Okay, so I do that. I clean that data set up and deduplicate it. So I've got 5,406 records there. Okay? And then what I'm going to do is split the data into 2 categories. One for low engagement, tweets that got more than 2%, less than 2%, and one for high engagement, tweets that got more than 2%. More than 2% of people that saw them liked, retweeted, or commented them. Okay, so that's my boundary. And I basically label my data high or low by splitting it into 2 sets. See where we're going? This is my training data. Okay, I've got samples that engage well and samples that have low engagement. Okay? Store that data on S3. So for the purposes of this service, S3 is our data lake. It's where we put our data for processing. It's got excellent performance characteristics, by the way. So when we're really training at really high scale, we can get very, very high performant concurrent access to data. We can have multiple 10 gig per second streams from S3 into our algorithms that are developing our models, enabling us to access our data really fast. That's why we use S3. Anyone heard of Spark? It's a distributed processing framework that pretty much replaced Hadoop, if you've worked with Hadoop in the past. This allows you to marshal and distribute jobs over clusters of machines. You can ignore what I just said, because it also has within it some helpful libraries for preparing data in various formats. Okay, something else that is embedded within Spark. Not using the distribution part of the framework here. I'm just using it to create data which is in the right format for training, these SVM files, sparse vector matrices that we talked about earlier. So we create one of those, okay? And then we are going to hash our data, and we're going to clean up our data. So we're taking a tweet which looks like this. You sold me £799 a month from me. Do you get a finder's fee or something? That's my tweet. Who knows what that relates to? It could be from any time in the last 5 years. I have no idea. But we're converting that into this machine format that you can see here, okay? Okay, and then we're labeling it. The important part to look at here is this one at the front, which indicates that this one at the front here, which indicates that this is actually a high engagement tweet, okay? I have 8,000 features, each one of which represents words in the content. So what we're looking at is the vocabulary that's used. We're going to correlate the vocabulary to popularity. That's essentially what we're going to do with the algorithm. More cleanup and data prep, and then we're going to do our training. It should give you a clue as to how training works. We were talking about containers earlier, so we actually package up all of our training algorithms inside open source Docker containers. You can download them and run them on your own machine, laptop, on-premises infrastructure. We don't care. We're just trying to make SageMaker the most convenient place for you to run this workload. But you can actually run it outside of AWS using our IP if you grab the containers and run them locally. They expect the data in the right format, okay? And then we can spin up our training job with some specific characteristics that you can see here. Run our training job. 4 minutes later, that's completed. We can deploy our endpoint. A few minutes later, that's completed. And then we can start to send samples across. So sample here is whatever content you want, which you can see at the top. I can package that up, encode it. Oh, wrong cell, sorry. This one. This one even. I can package that up, encode it in the same format as the previous samples. You see it's another SVM there with just the whatever content you want. Those are the word numbers for the 4 words in the vocabulary with the counts next to them, 1, 1, 1, and 1. Ship that over to my inference endpoint, and I'm told that there's a 46.94% chance that that tweet will garner high engagement and that customers will choose to engage with it. That's it. That's SageMaker. I can do all that using a GUI, by the way. I really like showing the notebook. It allows you to see more of the data preparation, which would be hidden from you if we were using the GUI. But that's basically how SageMaker works. Machines are used at 2 points. When I use my training, I'm spinning up machines in a cluster with those Docker containers on them, providing environment variables that point at the source data, and then spitting out a model which is stored in S3. So that's one point where a virtual machine infrastructure is used. And then for inference, I'm actually running one virtual machine permanently for inference. And that will scale elastically if I tell it to do so, okay, adding more capacity and taking it away as I no longer need it. Okay, so that's SageMaker. And then for one extra credit demo, maybe, I'm going to send some audio here, so I hope my sound is on.
Please point your external webcam at the subject. Taking a photo.
Ooh, and there we go. Classic demo fail. Let's try again.
Please point your external webcam at the subject.
It did work in testing, I guarantee you. We'll see.
Taking a photo.
Okay.
I detected the following labels: crowd, human, person, conference room, indoors, meeting room, and room. I can see 10 faces. The first person is male. He is smiling. He looks happy. The second person is male. He is wearing glasses. He is smiling. He looks happy. The third person is female. She is smiling. She looks happy. The fourth person is...
Okay, so that is a very quick example of using those higher level abstracted services that I talked about. There's actually 2 different services in play there.
She looks happy.
Amazon Polly is dynamically generating all of the speech that you heard. There's no audio generation capability on the laptop. I'm sending text fragments to the API endpoint, and I'm receiving back MP3 audio, which is then played out from the laptop. You can tell this because the first person is male, he looks happy. The second person is female. Also, you can tell this with the inflect, a conference room, an elephant would be correctly voiced, okay? So we're using inflect to enrich the audio with enrich the text input with the right, what's the word? Pronouns? Prenouns, maybe? Yeah, whatever that thing in English is, we're doing that. And then the second component, of course, is the image recognition. So we're sending a base64 encoded PNG over to the endpoint on the first hit, and that's returning back the high-level metadata, conference room, indoors, people, okay? And if we detect people, we're sending the same base64 encoded PNG over to the same endpoint with a face detect request, and that's the thing that's extracting the facial metadata. I could also have ranged your age if I'd chosen to do so by extracting that from the returned object. Chose not to do so. Like I wouldn't do it to myself. I certainly wouldn't do it to anybody else. And that is super, super simple, okay? If you go to github.com/ianmass-aws, which I'll very, very quickly show you because I appreciate I'm almost out of time here. You'll find the source code for that demo is there. It's called Poly Recognition Demo. Like everything I do, it's written in Python. But if you jump into the code, you'll see just how simple it is to use these abstracted endpoints. Getting back the metadata structure about what's in the image, for example. There's no deep learning here, at least not on the client. We just create a connection object using the AWS Python SDK to the endpoint, encode the image and send it, and then we receive a JSON structure back which contains data about what's in the image, and that's it. So it's all pre-trained models that developers can just natively integrate straight into their applications with no operational overhead and nothing to develop and maintain. You just call the API and get results back. So that's the simplest way to get started with machine learning on AWS. But if you really want to dig into the detail, then I'd say SageMaker, there are example notebooks there. So even if you've got no knowledge of deep learning, no knowledge of how to use the tool, but enough smarts to read simple code, to read Python, which I'm sure you can all do, you can evaluate and learn from those notebooks how the system works. You can literally read through them, run them, see the results, and kind of reverse engineer from there back to how they've been created. It's a really good way to learn. Just spin up a notebook instance, which you can do for free for 100 hours, start those sample notebooks, and have a look at how they're actually engineered and built. Okay, fantastic. I really want to thank you for inviting me to speak today. You can find me on Twitter here at Ian with 4 M's, Ian M, Ian MM, and Ian MMM. They'd already gone when I joined Twitter, so I had to have 4. But you can actually email me at amazon.com where I have more control. It's just ianm@amazon.com if you've got any questions, you want any follow-up, you want me to avail you with some AWS credits so you can experiment with some of these services, just shoot me a note and I'm happy to help. I'll be here till 2 for any questions that you might have as well. Thank you.